First of all, I previously gave a lecture related to I2C in another course, and here I will very briefly explain it, assuming you are familiar with it. In I2C, you need a couple of pins. SDA is essentially the data pin, while SCL is basically the clock pin. Data is exchanged based on the clock, which is essentially determined by SCL. You can also set the clock, but generally on 100 kHz is used. There is a clock pin and a data pin, and if you include the power pin and ground, that makes 4 pins in total. However, in practice, only 2 pins are actually needed. And for addresses, you can set up to a maximum of 127 addresses. If the addresses do not overlap, multiple I2C components can be connected in parallel to the 2 pins. For example, in the case of Arduino, there are SCL and SDA pins, and you can connect up to 127 different types of sensors, such as sensor A, sensor B, sensor C, and various other sensors, to the same SCL and SDA pins. However, there are some cases to consider. If you want to connect the same type of sensor for use, you can refer to the datasheet. To see how the address can change from 3A to 3B, depending on which pins are set to high or low, there are components that work this way. For those components, you can set the selector pin to change the address to avoid conflicts. However, there are also components that do not have this option. There are missing components, which leads to duplication. In that case, a more efficient method is to simply give up on I2C and check if SPI communication is possible. If SPI communication is feasible, you can deactivate certain components using the chip select pin. So if SPI communication is possible, it would be better to use SPI communication instead of I2C communication. That's not it. It's better to check if you can change the address in the datasheet. Looking at the Arduino, in our case, we will be using the Arduino Uno, which has the SDA and SCL pins configured. As you can see, in the case of the Uno, the SDA pin is AA4 and the SCL pin is A5. For the Mega, it is pin 20 for SDA and pin 21 for SCL. And for the Leonardo Duo, it is set up similarly. You can connect according to these specifications. For this I2C related project, we will use a sensor called PM2008 for testing, which is capable of both UART and I2C communication. So, we will test this I2C communication with this setup, which includes the sensor part and a shield that is sold together. So, after plugging this sensor onto the shield, if you connect these pins as they are, SCL and SDA will automatically connect to A4 and A5 on the Uno, as we saw earlier. Then you can check it. Next, when performing I2C communication on the Arduino side, we use the wire library. In the case of the example, since it is basically included, you can see the file example, the Arduino Uno example, and if you look at the wire, there is an ice case scanner, whether it was a shield or you connected directly to the SCL. And SDA, the first thing to check is the I2C scanner. As I mentioned, I2C components can have up to 127 addresses. This means that each one has its own unique address. So, if you scan this and the address is found, then you are ready to communicate. If you searched and nothing comes up, it means there is a problem with the hardware connection. In such cases, you should check whether the communication voltage is correct, whether it is 3.3V or 5V, or if there is a level converter that allows for compatible voltages. Additionally, verify that the SCL and SDA pins are connected correctly, that the ground pin is properly connected, and whether external pull-up resistors or the resistor connection conditions required in the datasheet are met. It is a good idea to check these things. If the conditions are met and everything is set up correctly, when you run this scanner, the address value of the component should be accurately retrieved. For reference, the address value for the PM2008 is 0x28 in hexadecimal. When you run the scanner, it should detect 0x28. In my case, I have an Arduino and a PM2008 shield connected together. In this state, if you upload and then open the serial monitor, it will immediately display like this. Take a look at the code. It's simple. You can ignore the comments above. The wire library has been imported and it has been initialized. After that, you will have seen the serial initialization many times before. Then there's a variable for device verification. Since address 0 is not used, we check from address 1 to 127. Initially, when we use library, wire, begin transmission. It's a command to start communication, and the address value is included. After entering the address value, you either write to it or read from it. Here, we are just checking the address and preparing for communication, but we end the communication without doing anything. When ending the communication, we check whether the error value is 0, indicating normal operation, or if it is not normal. If the error value is 0, it means there were no errors with that address, so we are ready for communication. This is indicated by outputting that the I2C address has been found on the serial monitor or an error is displayed. Generally, if the error is not 4, it is not displayed and we continue counting. At the end, if the count is 0, it means no addresses were found, and if it is not 0, it indicates completion. This process occurs every 5 seconds. In any case, whether it is Arduino, another ST or TI, the first thing done when communicating via I2C is the I2C scanner. So, checking whether the communication is ready is almost the same across the board. It's just the commands that differ, or the API that varies, and we confirm it in this way. Next, let's take a look at the values that have been read. In the example from the file, there is a master and a slave in the wire library. Our Arduino acts as the master, while controlling I2C components and I2C sensors. So our Arduino is the master. However, if our Arduino is connected to a Raspberry Pi and the Raspberry Pi sends data to it, then the Arduino becomes the slave when it either receives or sends values, like giving or receiving values in the form of ice cream. But generally, we are currently operating under the concept that the Arduino is the master, and we are controlling and verifying the PM2008 sensor as the master, so you can click on Master Read. When you click on the What's Reader, you'll see that up to this point, everything is similar. However, it differs here with the wire request from command, which has two parts. One is the I2C address, and the other is the byte length, which is 7 bytes. After making this request, it is similar to serial communication. When the wire available message appears, you check it and enter an infinite loop. During this time, you read 1 byte at a time and output it like this. So, this code requests 6 bytes from an I2C component with the address value of 8, retrieves it and outputs it 1 byte at a time. Now that we've seen how to read, let's take a look at writing. If you look at the example in the file for the wire writer, the initialization part is similar here as well. The difference with wire begin is that, as you saw earlier when we scaled, we use wire begin transmission to enter the address value, and here we have arbitrarily entered a file. Then I used wire write to input the text value here, but there are actually 5 characters. So after converting, we have 5 bytes. and then the part corresponding to byte X goes here, which means we are actually sending a total of 6 bytes to the I2C component and finishing the transmission. After that, we increment X and continue sending in this manner. So, I2C is simple. It communicates by reading a certain number of bytes from the specified address and sending a certain number of bytes to the component at that address. In this session, we briefly looked at the example of the wire library for I2C on Arduino. Next time, based on the PM2008 sensor we covered this time, we will actually use the wire library to request, read, and write the necessary values, even though there is already a PM2008 I2C library available. Then I will see you next time.